Next is Robert Morehead.
Hello, I'm Robert. You may remember me from such emails as "you got a poster talk," or "hi, my registration didn't go through. Can you please tell me what's going on?" I've been the ERESS webmaster for, well, since before we actually had a date. So I just want to say I'm really glad to see all of you here, and I hope you guys are all having a really great conference. We put a lot of, the whole organizing committee put a lot of really hard work into having this happen, and so far so good. It looks like we're having a really good conference. I hope you're all having a good time. All right, so I'm the last talk before we go into poster pops in our poster session. So I erred on the side of brevity, so maybe we'll get a little ahead of schedule here. So what I want to do is talk about the implications for the false positive rate in Kepler planet systems by looking at the transit duration ratios in the Kepler multiple systems. So the work I'm talking about today only applies to the multiple planet candidate systems that we see in Kepler. All right, but before I go into that, because we now have gotten to the point where the Kepler data, we've gotten so used to seeing it and working with it that we kind of forget where it comes from. So one thing I want to kind of remind you of is just how large the plate scale for Kepler is. It has, each pixel in Kepler is 4 Arctic pixels. Don't you hate it when you notice the autocorrect typo right before your talk? Yeah, so not 4 Arctic pixels, although it is very, very, very cold in space. Each pixel is 4 arc seconds. Then we have several pixels that make up the photometric aperture that we actually do the photometry with. What this means, so this is actually from a Kepler DB report you can download from the Exoplanet archive. This is an actual system. I think this is Kepler 296, right? It's 296. This is actually a 5-planet system. I'm getting back. So one thing I want to point out is that there is actually a lot of room in there, because instead of using a telescope that has this really large plate scale, if you go to a kind of a more famous space telescope like Hubble and take a look at what's actually there, you'll notice that star is actually 2 stars. And so this red box is kind of that's the original photometric aperture from that 1/4 of data that we just looked at. So there's a lot of room in the Kepler data for blend scenarios, for false positives to work their way in. Now, half the stars that are in the galaxy are in binaries. A lot of these things are going to have something nearby that we may or may not detect. Now, we can get a lot of mileage out of the centroids, but even if we have good centroids and we don't have good centroiding for all the Kepler targets, there's still lots of room where we can have these false positives. So that's one thing that I've been concerned about with the Kepler multis. Now, we expect the Kepler multis to be a really good sample, right? There's other papers, other work that shows just by kind of like going the probability of being false positives all cramming together in a system, that we see a system with lots of multiple planet candidates, that they're probably not false positives. That's good, and that's what we expect. But if you actually want to know for individual planets, we actually know that these are real planets, it would be good to look at them with a little more effort. Let's look at them a little deeper. So one thing we can do is we can take advantage of this fact that we can write the stellar density in terms of the orbital period and the transit duration. So we can actually normalize the transit duration by the period and use that to get a quantity that's proportional to the stellar density. Now, if we have multiple planets, if we have 2 or more planets in a system, then we have several pairs of planets that should be probing the same stellar density. And so if we take a ratio of those normalized transit durations, that parameter, which we call xi, which is one of the accepted pronunciations of that, should be close to 1, right? It should be 1, right? If they're measuring the same stellar density, no matter what the actual error in this terms are, how will we know the stellar radius or not, it should be 1. Well, okay, but planets are more complicated than that, right? Although we expect the multis to have low eccentricity, they may still have some eccentricity. Especially maybe in the 2-planet systems, which may be more dynamically hotter than the higher multiplicity systems. So that's going to be an effect into our transit durations. The other thing too is inclination. Even if they're transiting, they could still have a very high impact parameter. And one thing that we don't really measure very well with the Kepler data are those impact parameters. And so to actually use this to do something useful with it, we need to kind of appeal to simulation. And so that's what I've been working on. So the technique I'm using is basically Monte Carlo simulations kind of crammed into Bayes' theorem to assign a probability that for every pair of planets that we see in a Kepler multi, what's the probability that those are actually planets? So basically the idea is you take a pair of planets and then you simulate it as a pair of planets around the target star. Great! Okay, you're done. Oh, okay, but wait, it could be a background eclipsing binary. Okay, so let's make one of the planets a background eclipsing binary, and one of the planets around the target star, simulate that and see what we get. Oh, but now, wait, what the inner planet's now the eclipsing binary, let's simulate that. And then, oh, what if it's a hierarchical binary? Or what if it's a planet around one star and then a planet around the other star? Oh my goodness. And you see why this project takes so long. And so that's what I do. So I simulate each pair of Kepler multis as a true planet system and as a suite of false positives. And so this is the actual distribution for those normalized transit durations for each of those different cases. So here, this nice pointy one here is for an actual two-planet system around the target star. The vertical line is the actual observed value, and then the shaded region is the error bar, so we just integrate this distribution over. So then, if we have two planets orbiting different stars, kind of what you'd expect, right? Stellar density, especially in the main sequence, are going to be pretty close, so it's similar, just some broadening in there. But where it really gets useful is where you have background eclipsing binaries or hierarchical binaries. Unfortunately, thank goodness, these distributions come up a bit different. So we actually do get some statistical power to start discriminating between these different cases. So, what do we get? So, if we this is a kind of a weird histogram. One thing that you'll notice is the bends are not even. So I wanted to kind of accentuate the borderline here at about 99% probability where things start getting interesting. And you might think about, you know what, I'm going to go ahead and just slap a Kepler number on that. And so the bends, although they're plotted the same width, these are very, very different widths. And so these are, each one of these, this histogram is made up of the probabilities of individual pairs in the Kepler multis, and just what that distribution of probabilities for being two planets orbiting the target star. Okay? So what you see is just from this work, and one thing I didn't mention is that to do this, we're just taking the bulk properties coming from the Kepler catalog. So we're not using any actual additional observational information we may have about the system. These are the results if we say, okay, all we know is what we got from the Kepler spacecraft and what we know from like stellar models and things like that. So here you go, great, we have two planets orbiting a target star. We see those have a fairly high probability, but only 90%, you know, that's not so great. But what if we say, okay, well, what's the probability that they're planets orbiting the same star, but it's not necessarily the target star, it's not the star we think it is? Well, then the probabilities start getting pretty good here. We start getting 99, we get either about 99.5, we can start thinking about assigning Kepler numbers to that. Now, fortunately, a lot of Kepler numbers have been assigned to the multis, and so that's kind of what you're seeing here, is a lot of these are actually things that are Kepler numbers. But the important thing I want to point out here, so if you look at compare the difference of these, there's maybe for a given pair of multiple planets in a multi-system, maybe on average about a 10% chance that they may not actually be on the target star. They're actually a multiple planet system, but they could be around another star that's blended in the photometric aperture. The problem with that, if the stars are actually orbiting a different star than you think, and you based your derived parameters of the planets from what you know about the host star, those parameters could be wrong. And so a lot of what could be what we're classifying as super Earths or even Earths could be larger planets. So that's kind of the downer part. But then, okay, so let's ask the question, well, I don't care if they're actually around the star I think they are. I don't care if they're actually a real multiple planet system. The question I'm interested in is I just care if they're planets or not. That's the important question, right? The answer is, oh yeah, they're mostly planets. They're totally. To actually get a eclipsing binary to look like a false positive when you have other planets there, and to get the duration ratios work out, it actually ends up being a fairly rare case. So the bottom line is, as we'd expect, Most of the Kepler planets are actually most of the Kepler multis are actually planets, but a few of them may be misfocused. It may be around a different star than what we think it is. And I will stop there since I'm out of slides.
Since you're talking about the idea of it being possibly around another star, is this also taking into account, is that possibly having other stars in there that you're going to have transits look shallower than they should be?
Absolutely.
Okay.
Yeah.
Are you folding in what you can know about the star from Morehead?
What you know from the stars about?
You can get a constraint of stellar density based on the flicker.
No.
About doing that?
No. None of that. No flicker.
Because that might also figure out which star the planet's orbiting. And it obeys your rules of using only what's in the kit and like that.
That's true. So that would be, hey, Eddie, that's just down the hall. That's a good idea. Thanks.
So if you, the calculated probability that it's not actually around the star that we think it is, do you have a method to go about finding out which is the actual star? Or just that it's not the target one?
So what I'm doing now only is just assigning a probability of those cases. Once you know that probability, if you want to include other information like flicker or any other follow-up information, then there's some stuff you can think about doing. So looking at the durations, looking how they change, especially if you see one, there may be a few of those where you see one pair spike kind of off differently when you compare them against each other stars in the multi or other planets in the multi, but then together they look pretty good together. So maybe I've been kind of in the back of my mind thinking about ways that you could start using that to distinguish.
If there's a high probability that it could be orbiting a different star, how constrained are the characteristics of those two stars then? I mean, do we know those two stars' properties well? I would guess not.
Right. So probably not. Right. So if you have more follow-up and you know there's two stars, right, and like with Kim's paper where they went with Hubble, saw that there were two stars there, and then you can start. Okay, now we know that there's two stars. We can start considering those properties separately. So the idea is that these are things that are just these big, huge, poster-sized, giant megapixels, and this is basically really a first pass at those individual pairs.
I was just curious, are there any cases where it's known that they're individually orbiting different stars that with adaptive optics or HST, whatever, high resolution follow-up?
So I know Tom Barkley and collaborators just did actually on 296. Just did a paper where it showed that it was probably on the primary, which is interesting because I was betting that about 3 of them were on the secondary. But I may have missed the paper, but I don't know if anyone has shown conclusively whether they're for sure where there's been multis where there's definitely been misplaced.
Anybody else? All right, thank you, Robert.